Thank you. Yes, this is about Euler and his amicable numbers. And as I think I said at lunch, if you were there, I'm going to break this into two parts, a sort of introduction to Euler, and then some Eulerian mathematics about amicable numbers. So let us begin. This is Euler. You've probably seen this picture. The official name of this is the Hondman portrait. The unofficial name is Euler emerging from the shower. Right? It looks like he just took a shower. If someone was going to come over and paint my picture, I would not wear this, I tell you. But this is what he chose to wear. So, okay. Now let me give you a quick bio. Born in Basel, Switzerland, 1707. By the time he was a young teenager, he was studying with Johann Bernoulli, who happened to be in Basel at the time. And this is quite fortuitous because Bernoulli was probably the greatest living mathematician at that point, or active mathematician. Newton was still alive, but he was quite old. Leibniz was gone. Jakob Bernoulli, his brother, was gone. So here is a great mentor for the young Euler. He graduates from University of Basel in 1722 at the age of 15. His first appointment was to the St. Petersburg Academy in Russia in 1727. Now you know that in Europe at this time, the great courts had these academies, collections of writers and musicians and scientists that were meant to enhance the reputation of the nation and the court. And you know, there was the Royal Society in London, the Paris Academy, the Berlin Academy, and in Russia they wanted one. They were just starting up the St. Petersburg Academy, and they get Euler to come and be one of the early members. So he was quite young at the time, but it was a good choice. He stays there until 1741 when he's lured away to the Berlin Academy under Frederick the Great. And you know, it was like he was a great sports star that changed teams or something. So now he's at Berlin where he meets Voltaire, D'Alembert. But eventually he gets tired of that and goes back to St. Petersburg and finishes his career in Russia and stays there until his death in 1783. Now, in terms of just a geographical life, this is pretty constrained. It wasn't what he did in the physical world, but in the mathematical world that made him so great. I should just mention, these dates are almost exactly those of Benjamin Franklin. So if you want a comparison here on this side of the ocean, Euler was almost exactly Franklin's contemporary, although they never met. They should have. He's buried in St. Petersburg. There's his tomb. The story is he was originally buried in St. Petersburg, then he was buried in Leningrad, and now he's buried in St. Petersburg. So, on the personal side, he was married and had 13 children. But the story is actually rather sad because this was the 18th century and childhood mortality was a very serious problem. And of these 13 children, only 5 survived to adolescence. So it would have been a very sad household so much of the time. Euler was blessed with a phenomenal memory. All reports are that he could memorize anything. Books, plays, poems, and tables. So where other people had to look up a logarithm, he could just remember it. And this would serve him well when physical infirmity strikes, because in the 1730s, he lost vision in his right eye. And the story is this was some kind of infection, we think now, that got away. And now it could be cured with an antibiotic rather easily. But it not only took his vision, it destroyed the eyeball. So his eye just shrunk. So it was of no use. So he stops working, right? Wrong. He keeps going. That doesn't stop him. He keeps going at full speed until 1771 when he loses vision in the other eye. And this was a cataract, which is easily fixed today, but not then. And so what they tried was surgery. And you don't even want to think about eye surgery in 1770. Yeah, right. Newton could bring his bodkin, yeah. But, they didn't have Newton, but they had an eye surgeon. But this was a horrible experience. It was painful, and it failed. And so now Euler's essentially blind. So he gives up, right? Wrong. His output does not diminish. He keeps going just as strongly as ever, and thereby becomes, I think, the great inspirational story in mathematics, that he did not let the physical ailment stop him. he would just come into a room and dictate to a table full of people writing furiously. He would dictate his mathematics even though he couldn't see. And he was using this memory where he had this ability to sort of see things in his mind's eye. If a new paper came out from D'Alembert or Lagrange, they'd read it to him, and he'd just absorb it and then make suggestions. So he's like Beethoven. Beethoven can't hear, but he's writing great music. Euler can't see, but he's writing great mathematics. And if you don't believe me that his productivity did not diminish, I should point out that as a blind man in 1775, he published 50 papers, a paper a week. Now that suggests what is a truism, and that is that the quantity and quality of Euler's work are almost hard to believe. It sounds like science fiction. And let me address these separately. The quantity of his work. All right. Get this. He died in 1783. But he wasn't done publishing. In the years between 1783 and 1830, 47 years, he managed to publish 159 papers. But he still wasn't done. He had a great year in 1844 when he published 61. And then there was a little blip in 1849 when he published 8 more. So if you add these up, he published 228 papers while dead. No other dead mathematician has ever published that many papers. It's amazing. But these are things they found in his desk, or things that were in press, or things that were in his notebooks, and they just kept coming to the surface, and his productivity expanded. In 1910, Gustav Enström decided to catalog all of Euler's published works, and it came out at 866 books and papers. And Enström, dredges these up, finds them, and then writes little descriptions of each one, little descriptions. And the catalog is 388 pages long, just the catalog describing Euler's work. The Swiss Academy of Sciences then begins publishing all the work, and it's called the Opera Omnia. The first volume comes out in 1911. The volumes are like this. They're big and substantial. This is the one where the Amicable numbers paper is. But you can see that's heavy, So this comes out in 1911, and then there's one in 1912, and they keep coming. At the moment, there are 75 volumes in 4 series and 25,000 pages, and they're not done yet. They're still coming out. So this has 74 cousins, and if you stack them, it would go above the ceiling. It's amazing. The grandchildren of the original editors are old, and they're still working on Euler. He's kept the Swiss Academy busy for a century and more. There's nothing like it. Now, in terms of quality, well, that's a little harder to measure, perhaps. And part of this will come out, I think, when I show you some of the things he does. But here's one thing I did. I went to Math World. You might know this. This is a site. And you can put in a term. This is like a math dictionary. And I put in Euler to see how many concepts in mathematics that are famous enough to get in the dictionary are attributed to him. And out came 96 entries. From the Euler product sum formula to the Euler identity to the Euler line to Eulerian integrals and so on and so on. That's a huge contribution of important ideas. And just for comparison's sake, Gauss, I typed him in, 70. Cauchy, a piker, 33. And some people fare even less well. Okay. Matthew, do you have a question? How many? I do not know how many there are total. No, but that's as far as I know, that's the most things named after any one person. Okay, so the quality is good. Now let me show you some of the things he does. So here's one. He gives us the number E in 1748, and here it is. This is how it first appears. It's he's writing. He says, for the sake of brevity, we place the letter E to be this number, 2.7182818288459, etc. He loved calculating things out to many, many places. So there it is, and he's going to call this E for the sake of brevity. He says, which therefore denotes the base of the natural or hyperbolic logarithm. So he certainly knew what it was. And if you want to calculate it, he says, here you go. Here's your formula. If you want to do this at home, it's 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3. He didn't have the factorial notation, but there it is. That's e to the x, where x is 1. And that converges very fast and allowed him to get this to a very high degree of accuracy. Now, suppose he'd done nothing else. This still would warrant a sentence or two, you know, in the math history books to give us e, but he did so much more. Here's one, the Euler identity. I mentioned this at the lunchtime talk. E to the ix equals cosine x plus I sine x. And I showed you one of his proofs of that. Well, here's how it appeared for the first time. Notice he didn't use I at this stage. He was still writing square root of minus 1. And he was using v instead of x. And he wanted to make this positive, so he put a plus sign there, I guess. And curiously, he put a period after cos and sin, because these were abbreviations. Cosinus, sinus. And you didn't want to write the whole word out, so you just abbreviated, but you had to put a period in. We have now dropped the period, but we have otherwise kept the notation of him. And as everybody knows, if you take that and stick in x equals pi, you get, I mentioned this today, e to the I pi plus 1 equals 0, always regarded as or often regarded as the most beautiful formula in all of mathematics, because it has the 5 great constants of 0, 1, ei pi all together in one formula. The dream team of constants all together, you know, right there. It's amazing. It's so amazing that somebody wrote a poem about it, which I shall now inflict upon you. So here it goes. E to the I pi plus 1 equals 0 made the mathematician Euler a hero. From the real to complex with our brains in great flex, he led us with zest but no fear. Oh. Okay, so it ain't Shakespeare, but it's okay. Okay, what else? Well, he gives us in 1752 the Euler polyhedral formula. V plus F equals E plus 2. A polyhedron, of course, is a solid body, a three-dimensional body whose faces are polygons like a cube. And V is vertices, F faces, E edges. And if you look at the cube, you see this works. There's 8 corners, 6 faces, think of a die. 12 edges, 8 plus 6 equals 12 plus 2. Okay, that's pretty obvious. But what Euler says is this works for a vast number of solid bodies of polyhedra, such as pyramids, such as icosahedra. And he proves this, and this becomes, you know, one of the great results from Euler, and a foundational concept in so much of later mathematics, the Euler polyhedral formula. So, you know, somebody wrote a book about this, just a whole book about this formula a couple years ago, published by Princeton. So, you know, this is a biggie, but Euler was a little more circumspect about it. Here was his review of this. He said, I find it surprising that these general results in solid geometry have not previously been noticed by anyone, so far as I am aware. How could anybody have missed this? V plus F equals E plus 2, he says. Well, that's because not everybody was Euler, right? He could see things that others just didn't. Okay. There's the Basel problem, another major achievement of his. This is 1734. The issue is this. In 1689, Jakob Bernoulli, who was Johann's brother, Johann was Euler's mentor, challenged the mathematical community to find the sum of that infinite series, the reciprocals of the squares. What does that add up to? And Jakob is writing from Basel, Switzerland, so this came to be known as the Basel problem. Now, I should say this, that Jakob Bernoulli was no slouch with adding up infinite series. He was very good, and in 1689, he wrote something called the Tractatus de Seriebus Infinitis, the treatise on infinite series, in which he sums all kinds of sophisticated infinite series. And let me just show you one. Sum k goes from 1 to infinity. He didn't write it this way, but this is our notation. Of k cubed over 2 to the k. Now, well, he's looking for exact answers, not just, yes, this converges, but exactly what it converges to. And I should say that I've been all over the world and asked this question, and nobody could answer this, you know, what this comes out to be. And it's not 1 or 0 or infinity. But the actual value of this, as Bernoulli shows, you're not going to believe it, 26. That's exactly what this adds up to. That's correct, right? So there's a problem for you if you want. But the point is that Bernoulli was good at summing these series. And you can sense his frustration that this series, which looks considerably simpler, he couldn't do. He couldn't find the exact answer. And he writes in the 1689 paper, if anyone finds and communicates to us that which has thus far eluded our efforts, great will be our gratitude. Please, can somebody answer this for me? Well, that's 1689. A generation passes. Nobody can until Euler comes along. And in 1734, he gets the famous answer of pi squared over 6. Still, one of the strangest formulas in all of mathematics. Now, Euler does this by basically factoring the sine function, writing it as an infinite product and an infinite sum, and matching coefficients. And that's his first proof. But Euler being Euler, he comes back and revisits it. And in 1741, he does it with integral calculus. A very nice argument using the arcsine series. And then he revisits it again in 1755 using differential calculus. And 3 applications of L'Hopital's rule to get this to fall out. He finds a bizarro formula where if you put 0 into one side, you get the series. And if you put 0 into the other side, you get 0 over 0. And he uses L'Hopital's rule and he gets 0 over 0. And he uses it again and he gets 0 over 0. And most of us would have gone home by then. But he uses it again and he gets pi squared over 6. It's an amazing argument. And just as a little aside here, on Pi Day, the math club here at Princeton has asked me to come and talk about pi, the history of the famous constant, March 14th. And what I plan to do is talk about the crazy people involved in pi for the first half. But for the second half, I'm going to derive this, as Euler did, with 3 uses of L'Hopital's rule, the most spectacular example of his symbol manipulation that I know. Okay, so anyway, that made him famous. He was very young at the time. He was in St. Petersburg. Nobody quite knew who he was before this, but after he did this, everyone in Europe knew this guy, Euler. The product sum formula, 1737. Here it is as it appeared in his journal, in a journal. I don't know if you can see this. He has P equals 1 over 1 minus a half times 1 minus a third times 1 minus a fifth times 1 minus a seventh. He says that will be this, P equals 1 plus a half plus a third plus a fourth. And if you write this in our notation, what he's saying is the harmonic series is this infinite product over the primes. And he gives an argument to justify this. Now, wait a minute. You say, hold on. This diverges. This is infinity. This is diverges. This is infinity. He's telling me infinity equals infinity here. This is, maybe a dumb thing to do, a bad thing to do. Well, not in Euler's hands. Because starting with this, he reasons in a brilliant fashion and addresses this question. What happens if you sum the reciprocals of the primes? Converge or diverge? Now, if you sum the reciprocals of the squares, converges to pi squared over 6, because there's not that many squares. If you sum the reciprocals of the evens, diverges. What if you sum the reciprocals of the primes? I don't think anyone had asked a question like this until then. And it sounds very modern to me. Not from 1737. Well, he takes it, he applies that product sum formula, and he gets the answer. And you probably know it, it's divergent. The primes are sufficiently plentiful that diverges. And that's a neat fusion of number theory with primes and analysis. And indeed, André Weil said, one may well regard these investigations as marking the birth of analytic number theory, a subject which is now, of course, fabulously rich and vast. But you could trace it right back to this. Okay, now I want to get to my amicable numbers, but just 2 other things real quick. Here's a curiosity. This is not important, but this is something Euler did that I found interesting. The challenge was to find 4 whole numbers, the sum of any 2 of which is a perfect square. Now, I have to amend this. This is easy. The numbers are 8, 8, 8, and 8. Any 2 of them sum up to a perfect square. So this should say different whole numbers. Find 4 different whole numbers. No matter which 2 you add, you get a perfect square. If you think that's easy, try it. It's not so easy. Now, here's what I think. Suppose I'm going to do this just off the top of my head. So I start with 1. Okay, now I need a number to be my second number, add it to 1 to get a perfect square, so I toss in 3. I need a number to add to 3 to get a perfect square, so I toss in 6. But what happened? Now the 6 and the 1 don't add up to a perfect square. So you go back and change this, but then the 10 and the 3 don't add up to a perfect square. So you're like trying to juggle these things, and it's hard to do, and you got to do 4 of them. So if you try your hand at this just intuitively, you're going to be in trouble. Right? But Euler applies his great insight, and he finds these 4 numbers. 1, 2, 3, 4. And they work. Those numbers add up. Any 2 of them add up to a perfect square. Now, you see this and you think, this is magic, this is crazy. And then he tells you what he does. Oh, yeah, I see. I get it. And it's not magic. It's just Euler. But these work. One last one before we get to my amicable numbers. Another curiosity. Everybody knows how to factor polynomials into first and second degree factors, right? So x squared minus 1 breaks into 2 linears. X to the 4th minus 1 breaks into a quadratic and 2 linears. In the 18th century, people were trying to prove this result. Any real polynomial of any degree can always be factored down into the product of real linear and or real quadratic factors. And that's what the fundamental theorem of algebra looked like in the 18th century. There was no complex numbers in it. It was just about real polynomials. And of course, you can't shatter them down into just linear pieces, but linear and quadratic. Now, so that was a challenge. That was the conjecture. And you could do this for any polynomial. And Euler tried to prove that, but his proof failed, actually. So he wasn't perfect. He got that wrong. Gauss eventually proves it. But somewhere in Euler's lifetime, he gets a letter from Nicholas Bernoulli, who said, that's not true. You can't factor all real polynomials into first and second degree pieces, because I have a 4th degree that you can't factor. And Bernoulli sends this to Euler, that one. X to the 4th minus 4x cubed plus 2x squared plus 4x plus 4, says Bernoulli, is irreducible. Can't break it down into 2 quadratics. If that's right, then the fundamental theorem is dead, right? Well, Bernoulli couldn't, but that doesn't mean it can't be done. Euler thought about it. He says, I can factor this into 2 quadratics. Here's the first one, and here's the second. Now, you say there's two reactions. One is, this can't be right. I mean, these have square roots within square roots. Are you telling me if you multiply these 2 back together, you get that simple quartic? Well, I confess, one afternoon I had nothing better to do, and I multiplied these back together, and it works. This is right. So he's right. The second question is, how on earth did he come up with this? How do you do this? Is this final proof that he's from outer space, or something? But then you read it, and it's very clear. He tells you what he does. Oh, yeah, I'd have thought of that, you say. Well, I don't know. He makes it seem easy. But there's a method there, of course. OK, well, so Euler was pretty good. And he's pretty good in number theory when he comes upon this concept of amicable pairs. So the definition is that whole numbers m and n are amicable, which means friendly, right? If each is the sum of the proper, I should say, whole number divisors of the other. And by proper, I mean smaller than the number. So this is the concept. Friendly numbers, amicable pairs. Now, if you've ever seen this concept, I'm sure this is the first example they've given. This is the smallest one, 220 and 284. Now, what I have to do then is take the proper divisors of 220, all the whole numbers that divide into 220 but aren't 220. And there they are, 1, 2, 4, 5, 10, 11, 20, 22, 44, 55, and 110. If you look on the yellow sheet, you'll see them. They're right there. You add these up, and you get 284. Now, you take 284, and you look at all of its proper divisors, all the whole numbers that divide into 284. 124, 71, 142. Now, 284 does, but that's not proper, so that doesn't count. You add those up, and you get 220. I'll mention in a minute. Yeah, this goes way back. So each of these is the sum of the proper divisors of the other. It's a strange reciprocity. It's kind of weird. It's completely useless, right? There's no way this is going to help your refrigerator run any better. It's not going to make money on Wall Street. But it's what number theorists love, right? This kind of fascinating connection here. True story. I have a friend, it's true. He likes math. When he got married, he gave his wife a bracelet with the number 220 on it, and he has a bracelet with the number 284 to symbolize their friendship forever. They're lasting love and friendship. It's really nerdy, right? But it's really sweet, right? So there's an idea for you if you need a present for somebody. Okay, now to Peter's question, what's the history of these things? Well, the Greeks knew this pair. They knew 220 and 284. People think they just stumbled upon it. It was probably just luck that they happened to hit upon this. But remember the Pythagorean philosophy that whole numbers were sort of almost metaphysical entities. Number is all. We're going to study these things, almost worship these things. So this was really perfect numbers also, right? That's right. Yeah. So perfect numbers. If you're self-friendly, you're perfect, right? So this was cool, and the Greeks liked this, and they sought other pairs, and they could find none. And nobody could until the 9th century, when the Islamic mathematician Tabit ibn Qurra found a rule that generated 2 more pairs. So now there were 3, the Greeks and Tabits. But apparently, this rule did not make it back to Europe after the Renaissance. So the people in Europe thought there was just the 1 pair, as far as I can tell. They didn't know about Tabit's work. And so it was considered a great achievement when in 1636, Fermat finds a new pair, 17,296 and 18,416. The sum of the proper divisors of 17,296 is 18,416 and vice versa. You can check that if you want. So Fermat finds this. He's very proud of this. He makes a big splash. Guess what? That is one of Tabit's numbers. He has just rediscovered something, although he didn't know it, but in fact he was going down the same path. Okay, now in the 17th century France, there was a great rivalry between Fermat and Descartes. They did not like each other. And here's Fermat coming up with a pair of amicable numbers, and now it's like Descartes' honor's at stake. He's got to find a pair of amicable numbers. So he goes to work on it, and 2 years later he finds this pair. 9,363,584 and 9,437,056. Each is the sum of the proper divisors of the other. If you really love your wife, you give her a bracelet with this number on it, then wow, think about it. Well, guess what? That's Tabit's other number. Descartes was just following the same path that Tabit had. So these are the easy ones. This is the low-hanging fruit of amicable numbers. And after this, for another century, nobody can find any more. And then Euler comes along in 1750, and in one paper, he finds 58. So the world supply goes from 3 to 61 in one paper. And he's multiplied the supply of these by 20. How did he do it? Well, that's what I'm going to show you. But he sees a pattern. He sees something that nobody before him had. And it shows up in this paper. And if you have your yellow sheet, I just copied this front page of this. The title is De Numeris Amicabilibus, on amicable numbers. And I put this on there mainly because I love saying the word amicabilibus. That is a great word, right? It brings a smile to your face. If you're ever feeling bad, just say amicabilibus. Okay. If you look here, you see 220 and 284 showing up. He's giving his little introduction. And then he goes on to explain how he's going to find dozens and dozens and dozens more. So here we go on the math part. The first thing we're going to do is introduce the Euler sigma function. This is where he introduces the Euler sigma function in this paper. And sigma of n is going to be the sum of all the divisors of n, including n. He thinks that is a better way to go than just looking at the proper divisors. Now, if you've had number theory, you've seen this. If you haven't, well, let's do an example. Sigma of 15 is the sum of all the whole number divisors of 15, 1 and 3 and 5 and 15. There they are. You remember, you count the 15. So that adds up to 24. This is a useful tool for characterizing primality. P is prime if and only if sigma of p, the sum of all the divisors of p is p plus 1. 1 more than p. So you get that. So it has that connection. But it's also going to be a useful tool for characterizing amicability, as we'll see. Euler realizes some things about it. For instance, if you have two different primes, excuse me, sigma of the product is the product of the sigmas. And again, real quick, if you haven't seen this proof, it's quite simple. sigma of PQ, you add up the divisors of PQ. There's not many. 1, PQ, PQ. Group the first two, factor Q out of the second two, factor 1 plus P out of both, and you get sigma of P, sigma of Q, because these are primes, and these are their sigmas. So it distributes across the product like that. And so if I wanted to do that sigma of 15 the easy way, I'd just say 15 is 3 times 5, and do sigma of 3, which is 4, sigma of 5 is 6, and you get 24. But Euler knew more than that. He knew that if the numbers were relatively prime, even if they weren't primes themselves, as long as they're relatively prime, then the same property holds. This is a multiplicative function. Sigma of AB is sigma A, sigma B. And this is a tool for breaking down complicated numbers and finding their sigmas. So sigma of 585, if I wanted that for some reason, which I do, you factor that into 5 times 9 times 13, relatively prime factors, split it into sigma of 5 times sigma of 9 times sigma of 13. Sigma of 5 is 6. Sigma of 9 is 1 plus 3 plus 9, which is 13. Sigma of 13 is 14. And you get 1,092. And I'm going to write that on the board here, because we're going to need that, believe it or not, in a minute. So sigma of 585 is 1,092. OK. Now, we interrupt this lecture to bring an aside to you here. I lied. Actually, Euler didn't write sigma of n. The notation he used in his paper was that. Bad idea, Euler. I mean, he was great with notation. But people said, no, that symbol is sacrosanct. We're not going to use that for anything else. So they put in sigma, and that's good. And here's another aside. I just learned this the other day. Somebody told me this. I hope this is right. This is fascinating. If you let Hn be the partial sum of the harmonic series, the nth partial sum of the harmonic series, then this statement, that sigma of n is less than or equal to h sub n plus the exponential function of h sub n times the log of h sub n, that statement for all n is logically equivalent to, everybody know? The Riemann hypothesis. Yeah. That is another version of the Riemann hypothesis. And what's so striking about it is this is so simple, relatively speaking. You don't need complex numbers. You don't need analytic extensions and the imaginary part. The real part is a half, and on the line, all that stuff that's hard to explain to people. This all lives in a very simple realm of sigma, Euler's sigma, and the harmonic series partial sum. And yet, if you could prove this, you'd get the Riemann hypothesis. Needless to say, nobody's proved that. But anyway, so sigma is kind of still around. Yes, that's right. Yes, that's exactly what we're going to be doing. Yeah, right. Yeah. So anyway, so sigma is still around. But anyway, back to Euler. Here's what he realizes. Now he's trying to characterize amicability in terms of sigma. He says if these are some of the proper divisors of the other, the proper divisors of m are sigma of m minus m, because sigma of m includes the m and you don't want to. And the proper divisors of n are sigma of n minus n. You don't want the n. And so those two conditions are what amicability means. But if you kind of put these together, you get this very neat expression that sigma of m is m plus n and sigma of n is m plus n. And so that is what he's going to go after. And if you can find m and n with that property there, you've got your amicable numbers. OK, so he says, here's what I'm going to do. He says, I'm going to assume a certain structure for these amicable numbers. Now, later he could assume different structures. But for this piece of the argument, he's going to say, let's suppose the amicable numbers look like this. M is A times P times Q. And N, the other one, is A times R. As I say, we can expand this, extend this later. But for now, this is the assumption. Suppose those are amicable. And let's say that P, Q, and R are primes, and different ones. And they're all relatively prime to A. So they have no common factor. So you've got an A times a P times a Q. That's one number. A times R is the other. OK, now remember the condition. sigma of m equals m plus n equals sigma of n. So the first part of this he exploits is that. Just take the two ends. Sigma of m equals sigma of n. That would have to be true if these are going to be amicable. Stick in these values, and you get sigma of APQ is sigma of AR, because that's what m and n are. Now, use the multiplicative property. Sigma distributes, or moves across here, so you got sigma of A, sigma of P, sigma of Q is sigma of A, sigma of R. There go the sigma of A's. So sigma of P, sigma of Q is sigma of R, but P and Q and R are prime. So sigma of P is P plus 1. Sigma of Q is Q plus 1. Sigma of R is R plus 1. So the P, Q, and R have to satisfy that condition. Don't look elsewhere. That's where you want to look, there. Okay, now, he says, let's try to clean this up a little bit. So remember that. P plus 1 times Q plus 1 is R plus 1. He's going to let X be P plus 1. Change letters. And Y be Q plus 1. Okay, so then it follows that P is X minus 1, and Q is Y minus 1. Okay. And furthermore, remember we said that P plus 1 times Q plus 1 was R plus 1. So you put in here an X and a Y, and what you decide is that R is XY minus 1. So here's what he's accomplished with this. I'm going to put a star there. That's important. Instead of P, Q, and R, he now just has X and Y. He's lopped off a variable, basically, in his quest. I still don't see any amicable numbers around. Okay, now, he says, keep that in mind. Remember, sigma of m equals m plus n equals sigma of n. We exploited the exterior equality. How about the first one? Let's go back and remember that sigma of m is m plus n. See what we can squeeze out of that. So m was APQ and n was AR, so we stick those in. Move the sigma through on the left. So you get sigma of A times sigma of P times sigma of Q. And here, there's not much I can do but factor the A out. Now, I don't know, I can't cancel the sigma of A's this time. I'm stuck with this. But sigma of P is P plus 1 because P is a prime. Sigma of Q is Q plus 1. So we're to that. And let me put it up at the top of the screen here. So there it is again. So sigma of A is times P plus 1 times Q plus 1 is A times PQ plus R. But remember, X was P plus 1, Y was Q plus 1, and R was XY minus 1. So it says get the P, Qs, and R out of there and get the X's and Y's in. So here's where we are now. Sigma of A, P plus 1 is the X, Q plus 1 is the Y. Here's the P, X minus 1. Here's the Q, and there's the R, XY minus 1. And now inside that square bracket, simplify. And you'll see you get an XY minus an X minus a Y plus a 1, and then plus XY minus 1. So that condenses to 2XY minus X minus Y, and the 1's cancel. Okay, now what? Well, now he wants to solve this for Y. So if you look at this, there's almost all the terms have a Y in it. This minus AX doesn't, so that goes to the right, or to the left. And then what's left is a 2AXY minus a sigma AXY minus an AY, and he factors the Y out. And then solve for Y by dividing by that coefficient. And we get this. Y is AX over this guy, but in this one he factors the X out of the first two. So he gets sigma of A, or 2A minus sigma of A times X, and then minus A. And I still don't see any amicable numbers. Okay, but we're getting there. We're getting there. So let me move that up to the top. Now, time out here for a breather. Let's see. At this point, he has introduced M, N, P, Q, R, X, and Y. But hey, there's still letters left. You know, the alphabet has lots more letters. So it's time for more letters. So he does this all the time in his mathematics. He's always substituting a new variable for old. So he says, here's what I want to do. Look at A over 2A minus sigma of A. Now that's going to be a whole number over a whole number. Reduce it to lowest terms and call that B over C. New letters, B and C. I think these are the last of the letters you need. Okay, now, if that's the case, then 2A minus sigma of A is AC over B. Just solve for that. And put that in the square bracket there. So y is ax over, instead of the thing in the square bracket, I'm going to have ac over b times x minus a. There go the a's. Every term has an a in it. Wipe them out. And you'll be left with x over, what, c over bx minus 1 when you divide out the a. Multiply that through by b to clear fractions, and you get that y is bx over cx minus b. So there's y in terms of the x and the b and the c. And believe it or not, there's one more thing he needs, and then he's ready. And the one more thing he needs is, I would have never thought of this, of course. I would have never gotten anywhere here. But he says, let's look at this. cy minus b. That's the thing he really wants. cy minus b. Now, that's going to be c times y, but we just did y up here. So you put in bx over cx minus b, because that's y, and then minus b. Common denominator here is cx minus b. If you look at this, you've got a bcx minus a bcx plus a b squared. And so cy minus b turns out to be b squared over cx minus b. And what he does with this is cross multiplies. And finally, we got the big equation. cx minus b times cy minus b is b squared. And I'll put a double star there. Okay.
X and y are different from the prime by 1.
That's right. It's the numerator. Yeah, right. Yeah. That's right. That's right. So it's complicated. But you get down to this, and he said this is the key. Because when I do this, I'm going to do one in just a minute, b and c are going to be actual numbers. And b squared is just a number. And if it's the product of two things, there's only a few ways that can happen, a limited number of ways. You just check them until you find x and y that build back to give you p, q, and r that are primes, and you get your amicable numbers. So, he sees this as the salvation of this problem. Okay, so let me do one. So now the issue then is, where do you start? So so I guess I lied here. Let me give you the strategy. Okay, then I'll get to my example. Now this is on the back of the yellow sheet. If you want to follow along, because it's pretty complicated. You start with a. You then calculate a over 2a minus sigma of a, reduce it to lowest terms to get b over c. You use the double star equation. Cx minus b times cy minus b is b squared. So you can find x and y. Then you can find p, q, and r. And if they're all prime, you put them back together again and build your amicable numbers. M is APQ and N is AR. That's his strategy. So it all starts with A. So now, okay, here we go. I'm going to start with A equals 4. So the first thing you got to do is calculate A over 2A minus sigma of A, which is 4 over 8 minus sigma of 4. The sum of all the divisors of 4 is 7. 1 plus 2 plus 4. So you get 4 over 1, and that already is in lowest terms. So B is 4 and C is 1. Okay. Now you go, according to the yellow sheet, you go to this guy. Cx minus B times Cy minus B is B squared. I put in C equals 1 and B equals 4, and you get x minus 4 times y minus 4 is 4 squared, 16. Okay. Now, he actually makes a little chart now as he starts hunting for these guys, so I will do the same. So there's the critical expression. X minus 4 times y minus 4 is 16, and here's what you got to do. You got to fill in the chart to find x and y and p, q, r. And you're looking, remember, for primes. P, q, and r are primes. All right. So the first thing is, what two numbers multiply to be 16? That's with the x minus 4 and the y minus 4. Well, let's start with 16 and 1. 16 times 1 is 16. And now you start filling in. Now, if x minus 4 is 16, x is 20. If y minus 4 is 1, y is 5. All right, now you go after the primes. So p is 1 less than x, so it's 19, prime. Q is 1 less than y, it's 4, not a prime. Right? So this is out. This doesn't work. Now, most of them don't work. This is a dry hole. Most of the things he tries, you just throw away. You're looking for those golden nuggets where it all works. This time it didn't. Okay, so you try a different product. What else multiplies to be 16? Well, how about 8 times 2? So 8 times 2. All right, now we play the same game again. If x minus 4 is 8, x is 12. If y minus 4 is 2, y is 6. P is 1 less than x, so that's 11 prime. Q is 1 less than 6, that's 5 prime. This is good, but we're not done yet. We got to do R. This has to be prime. So that's xy minus 1. 72 minus 1 is 71. Yeah, prime. So now you've got it. This is what you're after. And now what you do is build your numbers back. M is A, P, Q, N is AR. A was the seed, 4. And so here we go. M is 4A times P, 11 times 5. And N is 4, the seed, times 71. And you multiply these out and you get 220 and 284. Good news, bad news, right? Good news, they're amicable. Bad news is that's the one they already knew. So that's not a new pair. But at least it shows that we're on the right track, I think. Now, if you start with the seed of 16, you get Fermat's pair. If you start with the seed of 128, you get Descartes. I don't think so. That's a very good question. Yeah, probably not. No, that would be interesting. Yeah. But notice what Fermat and Descartes, and indeed what Taubat were doing, they had hit upon a rule that works with powers of 2. 2 squared for 4, 2 to the 4th, 2 to the 7th. But then there's no others that work that are within any reasonable size that anybody could have done back then for the powers of 2, and so they were done. But Euler never assumed A was a power of 2. His whole theory is much more general, and that's where he unlocks the secret. So here comes a new one. So now pretend like it's 1750, and all you know are those 3 pairs. I'm going to show you how he finds a brand new one. And he uses 585 as his seed. Okay? So what do we do first? We have to figure out A over 2A minus sigma of A. So that's 585. Double that, 1170 minus sigma of 585. I've seen that somewhere. Oh, there it is, 1092. Right, we did that. So stick that in there. And you get 585 over 78, which isn't in lowest terms because 39 goes into both of those. So you reduce it to 15 halves. So B is 15 and C is 2. OK, now you look at this. Cx minus B times Cy minus B is B squared, where C is 2 and B is 15. And so that becomes 2x minus 15 times 2y minus 15 is 15 squared, 225. So this is the critical equation. I put it at the top. I make my little chart. And here we go, hunting for primes. All right, first thing you can try is 225 times 1. Now, follow me on this. 2y minus 15 is 225. So 2y is 240. So y is 120. X is 120. 2y minus 15 is 1. So 2y is 16. So y is 8. Back up 1. 120 minus 1 is 119. Prime? No, right? It sure looks like a prime, right? It's got a 9 on the end, but it isn't. It's divisible by 7 times 17. Yeah, so dry hole there. That didn't work. OK, back to the drawing boards. How about 75 times 3? If 2x minus 15 is 75, 2x is 90, x is 45. I think I see trouble coming already, but let me do the other one here. 2y minus 15 is 3, 2y is 18, y is 9. This is big trouble. As soon as I go after 45 minus 1, dry hole. OK. How about 45 times 5? That's another way to get 225. 2x minus 15 is 45. 2x is 60. X is 30. Promising. 2y minus 15 is 5. 2y is 20. Y is 10. 30 minus 1 is good, but 10 minus 1 isn't. So that falls through. Now you say, hey, wait, I'm sitting here. It's late. Show me an example where it works. This is going to work. The next one, I promise you, will work. So the next one is 25 times 9. If 2x minus 15 is 25, 2x is 40, x is 20. 2y minus 15 is 9, 2y is 24, y is 12. Back off from the 20, you get 19, prime. Back off from the 12, you get 11, prime. But there's still one more, xy minus 1, which is 240 minus 1, which is 239. And thank goodness that's a prime too. So we're in business. And now Euler builds his amicable numbers. Remember, the seed was 585, the A. So M is APQ 585 times 19 times 11, 122,265. and n is AR 585 times 239, 139,815. That's an amicable pair. And when he wrote these down, no one on earth had ever seen that one. That was brand new. And he did it, as I showed you, which is elementary. I mean, nothing here requires anything very sophisticated except an IQ of 4 digits or whatever he had. So this is how he does it. And then he does more and more and more of these. And if you want to do one of these at home, here's some seeds that he liked. He got 92 and 819 and 5733. These, a little bit. Yeah, there's certain things he doesn't bother trying, but these work if you want to try them. You know, there'll be a payoff, in other words. But then that didn't yield 58 new ones. He then goes back and rejiggers the M and N. He says, well, what if M is APQ and N is ARS, where these are primes? Now what conditions follow, and what new pairs can I get? And what if M is APQR and N is AST, and he gets some more? And by modifying the structure of these, he builds up his collection to blow the problem out of the water, as I say. Well, I don't know. I read this. I'm impressed. I think this is pretty good, you know, for somebody so long ago to be doing something so insightful. So there's just 2 slides left. The one is, my first reaction when I saw this was, amicabilibus, right? You know, I got to say my word, and yeah, okay, so good for him. All right. And the second thing is what I find myself saying often whenever I read one of these things by Euler, and I'm left dumbfounded. Way to go, Uncle Leonhard. Good work. Thank you. So yeah, so Peter's question is, what's the status of... Nobody knows if there's infinitely many. But what they have done, of course, is yes, they've turned the computer on. And I met a guy once whose PhD, he said, was finding 10,000 more pairs with the computer, you know. And I said, how did you do it? And he said, basically that way. But you see, Euler got stuck. What eventually limited him was, if you want to take sigma of A, you got to break A down into primes, and they didn't know which numbers were prime. I think, I'm not sure, but I think they think there's infinitely many, but you know, there's certainly tens of thousands that have been identified. I was going to say something. Oh yes, I gave this talk, a similar talk once at Baylor. And at the end, there was this little old guy sitting in the back, and he came up to me and he said, you know, when I was very young, I worked on this, and he was at Vanderbilt, and he commandeered their computer overnight. Now their computer in those days, you know, was like tubes, you know, and it filled 2 rooms. But he had it looking just by brute force. He didn't do the theory. He just started looking at the sums of the proper divisors and looking for matches. And he found the largest 5-digit pair. So they're both 5 digits. And with his computer search in 1958 or something, overnight, he found the largest pair. So I thought, wow, this is history, you know, right in front of me. You know, here we can go back to Euler, we can go back to the Greeks, but there's this guy at Baylor who was still working on it. So there's probably infinitely many, but nobody's proved that. Nor has anybody found a use for it yet, but that's okay. Yeah.
I wondered, like, in Euler, I know there was like one pair, I think it was like 1100 something, 1200 something, down by a schoolboy, like that. So did Euler ever find that?
No, and so the question is, this was quite amazing. It was the 19th century, right? And this little kid finds 2 4-digit ones, and you're right, it was 1159 and something, that no one had spotted, including Euler. It fell through his sieve here. He didn't catch it. And so this was astonishing. You know, this kid found these 4-digit ones that everyone had missed. And so then the question is, what happened to the kid? You know, did he win the first Fields Medal? And the answer is no. He became a shoemaker or something. That was it. That was his one mathematical foray. But he made a big splash by finding 2 4-digit numbers. Now they know all of the ones. You know, there's not going to be any surprises below a certain number. They checked. But that one fell through Euler's net. Matthew. Yes. Yeah. Frederick the Great. Frederick. Yeah, whenever Euler went to the Berlin Academy, Frederick the Great hired him. And so, yes, there was Frederick knew him. They talked to each other. Frederick didn't like him, amazingly enough. Frederick was a Francophile, right? A sophisticate. He liked Voltaire. He liked philosophy. Euler was a meat and potatoes kind of guy from Switzerland. You know, he didn't like that stuff. And so they didn't get along. They didn't hit it off. Euler was extremely devout. He was a devout Christian. And Frederick wasn't. And Voltaire certainly wasn't. And so, you know, there was friction there. And the sense is Frederick regarded Euler as a country bumpkin, you know, unsophisticated. Although he could fill more pages with mathematics than anybody else. But he wasn't in Frederick's league. He never met Bach, however. So. But it was a good time. That I don't know. The question was, did Voltaire dislike Euler? And I'm not sure. They were both at the Academy. How much contact they had, I don't know. But I do know Frederick, you know, when you're at the Academy and the monarch says do something, you have to. So sometimes Euler would be taken away from his math to go, you know, design a fountain or something for the palace. And, you know, that's what they wanted him to do. Frederick was actually quite cruel to Euler. You know, Euler's vision has gone. And Frederick took to calling him my Cyclops, which is really quite awful, right? So there was a real friction there and not a respect. And that's one of the reasons Euler went back to Russia. He was much more welcome there and got paid a gigantic amount of money when he went back. So, yeah. I don't know that Catherine did, yeah. Have you heard that she did? Yeah, I had heard that coming from Frederick, but perhaps wasn't nice, whatever. Thank you.